This is session B5, leading up to quantum mechanics, 1914 to 1924. Last session we did the Bohr model of the hydrogen atom, which was published in 1913. Today we'll explore three different discoveries from the decade 1914 to 1924, leading up to Schrodinger's equation publishing in 1925. We'll look at Einstein's spontaneous and stimulated emission paper from 1916, Compton scattering 1923, and the Dubrow matter wavelength from 1924. In 1916, Einstein published a paper, Emission and Absorption of Radiation in Quantum Theory. In 1913, the Bohr model for hydrogen had identified the discrete energy levels of hydrogen, and that the difference between those energy levels corresponded to emission and absorption lines from the sun and emission lines from the laboratory for hydrogen. In this paper, Einstein used classical physics and thermal equilibrium to draw conclusions about the absorption and emission rates. Let's assume a system with discrete energy levels in a surrounding environment of electromagnetic radiation. We will simplify this as two energy levels, 1 and 2, with the energy of the second level being higher than the first. And we'll assume the presence or absence of photons of electromagnetic radiation of energy delta E equal E2 minus E1, so a single frequency, which is delta E over H, so monochromatic radiation. Let ρ be the energy density of photons of this frequency only. We'll ignore all other photon frequencies. They have some effect, but this frequency F21 has the most effect. If the system is in state 1, and there are any surrounding photons of frequency F21, the system can absorb one photon and change to state 2. The probability for this absorption and change of state will be proportional to the photon energy density ρ. We say that state 2 is an excited state. If state 1 is the lowest energy state of all possible energy states, we would call it a ground state, but state 1 may also be an excited state. We only care that state 2 is excited relative to state 1. So if we're in state 1, this red line slanting to the upper right reflects time. Time is left to right on this diagram. We're in energy level 1. A photon of the right frequency happens to be present in our surroundings. We absorb it, so there is no photon to the right in future time. We absorb it, and we increase our energy from level 1 to level 2. That's absorption. If the system is in state 2, the higher level, the system can emit one photon in an arbitrary direction, any polarization, any phase, and change to state 1. This is called spontaneous emission, and its probability is independent of any prior surrounding photon energy density. So we have been in energy state 2, we drop into energy state 1, by emitting the correct frequency photon, which then has a life of its own. That's called spontaneous emission. This is a possible time to take a break. But Einstein identified a third possibility. If the system is in state 2, and there is a surrounding photon of the right frequency, F21, the system can emit one photon of exactly the same frequency, direction, polarization, and phase, and change to state 1. This is amazing. What's amazing about this is that the emitted photon is in the same direction, polarization, and phase as one of the surrounding photons. This is called stimulated emission. The probability for this emission and change of state will be proportional to the photon energy density ρ. Absorption and stimulated emission are reverse processes, both functions of the photon energy density. So we have been in state 2. There's a surrounding photon of the right frequency. We drop into state 1 and we end up with 2 photons of the same frequency, direction, polarization, and phase. Here's a different drawing of that. We are in state E2. There's a photon of the right frequency surrounding this atom. During emission, we have the photon and we drop into, in this case, level 1. And once we're in level 1, there are 2 photons, same frequency, direction, polarization, and phase. So Einstein wrote this paper in 1916. Decades later, stimulated emission will be the basis for lasers in 1960. And lasers are the most important part of what makes a CD player and a DVD player be able to read the disc. CD players came out in 1982 and DVD players came out in 1997. Also, the high-speed telecommunication links in the internet and the telephone system all use lasers. Laser is the acronym for light amplification by stimulated emission of radiation. Here's an image of multiple lasers of different colors. Many lasers emit just a single color. Some lasers are tunable so that they emit a single color at any given time, but can be electrically tuned to change what that color is. This is a possible time to take a break. So Einstein said, for a large ensemble of identical systems, in this case atoms, in thermal equilibrium at a given temperature, Einstein used classical physics to give relations between the emission and absorption rates as a function of temperature. We're not going to look at those equations, but we have the following takeaways. Stimulated emission can occur. Spontaneous emission must occur. An excited state cannot remain excited forever. The ground state can remain forever, but an excited state cannot remain excited forever. Even with no external electromagnetic field or photons, in a vacuum at absolute zero temperature, there's always vacuum zero-point radiation that can perturb an excited state into spontaneous emission eventually. You might read that the vacuum stimulates spontaneous emission. There's a rate for emission and a lifetime for each excited state. Excited state lifetimes vary from a small fraction of a second to 1,000,000 years. One example of excited state and lifetime is fluorescent glow-in-the-dark paint or patches. These absorb sunlight during the day, and at night they glow, typically a light green glow. That glow is from an excited state, and that excited state's lifetime is on the order of an hour or hours, which is how it can glow for so long. If we can use quantum mechanics to calculate either the spontaneous emission rate or the stimulated emission rate, we can use Einstein's result to calculate the other one. And this is used in quantum mechanics. We are not going to do it in this course, however. This is a possible time to take a break. Now we'll talk about Compton scattering. In 1923, an American physicist, A.H. Compton, working at the Washington University at St. Louis, published the paper, A Quantum Theory of the Scattering of X-rays by Light Elements. Compton found that when a beam of X-rays or gamma rays scatters in matter, for example, graphite, this scattering is a quantum phenomenon not explainable by classical electromagnetism. The X-rays and gamma rays behave as individual particles, photons, with their definite particle energy and momenta. The incident photon transfers a little of its energy and momentum onto some individual electron. It does not lose incremental amounts to every electron in the object. The photon gets scattered into some direction, any direction. It can be any direction continuously. It's not definite directions, not discrete directions. Mostly forward, almost all forward. And the scattering electron recoils, and it may get ejected from the material. Here's a diagram showing roughly the scattering. The beam comes in from the left. I'm showing it as this blue arrow. Almost all of the photons continue straight to the right, and that's this more solid black arrow. But Some photons get scattered into any direction. The bigger the angle difference from the forward, the fewer get scattered. So some will get scattered here, fewer here, fewer here, fewer yet, fewer, 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 fewer. This is a possible time to take a break. Now, Compton used X-rays for some experiments and gamma rays for other experiments, and his results are going to apply for both. I will generally say X-ray in the remainder of this video, but it applies to both X-rays and gamma rays. I just don't want to, in every place, say X-rays and gamma rays. So let's recall that the photon energy equals HF, frequency, or equally hc over lambda, wavelength, from Planck's results and Einstein results. And also the photon has momentum, P equals its energy over c, from special relativity. So another way to write the momentum would be h over lambda. When the incident photon gets scattered by a free, unbound, or loosely bound electron, conservation of relativistic momentum requires that the electron recoil. So it may have started with no momentum, but it picks up some momentum. Here's a diagram. Incident X-ray photon with wavelength lambda sub I for incident or initial, scatters on some unbound or loosely bound electron. The photon scatters, it changes its angle, and in order to conserve momentum, the electron has to go off with some momentum. And the electron therefore picks up kinetic energy, and therefore, for conservation of energy, the scattered photon has less energy than the original photon. And therefore, the scattered photon has longer wavelength, lambda sub s for scattering, longer wavelength than the incident photon. The energy in the scattered or secondary X-ray photon is less than the energy of the incident or primary X-ray photon by the kinetic energy of recoil of the scattering electron. So, FYI, this disagrees with low energy Thomson scattering. Therefore, the wavelength of the scattered X-ray photon is longer than the wavelength of the incident X-ray photon. Using the energy and momentum of a photon and special relativistic conservation of energy and momentum, Compton was able to find the distribution of the scattered radiation and also show that the wavelengths scattered minus incident, the difference between them has this form, where h is Planck's constant, m sub e is the mass of the electron, c is the speed of light, and theta is the angle that the scattered photon makes with respect to the incident photon. This term, h over mc, once we know Planck's constant, we know the mass of the electron, we know the speed of light, we can calculate this. When you calculate it, we get a length of 0.00243 nanometers. So smaller than an angstrom, smaller than the size of the atom. This term and this number are now called the Compton wavelength of the electron. This has units of length, but we won't think of it as an actual wavelength of wave phenomena, but it is always called the Compton wavelength. This is a possible time to take a break. The increase in the wavelength from incident photon to scattered photon is independent of the original wavelength. Scattered X-rays can have their wavelengths increased by a few percent because their wavelengths are larger than this number. Scattered gamma rays can have their wavelengths increased by up to 200% because some gamma rays have wavelengths comparable to this number. So this difference is big, comparable to or big for some gamma ray photons. Some of Compton's experiments were done with gamma rays of wavelengths 0.0022 nanometers, very close to this Compton wavelength of the electron. Takeaways for this course. This Compton scattering is a quantum phenomenon. It's not explainable by classical electromagnetism. Though X-rays and gamma rays are certainly electromagnetic waves, for this scattering, they behave as individual particles, photons, with their definite particle energy and momentum. One X-ray or gamma ray photon scatters off one individual electron, not every electron in the object. Relativistic energy and momentum are conserved, and special relativity is used to determine the scattering. The scattering electron acquires kinetic energy from the incident photon, and so the scattered photon has longer wavelength than the incident photon as a function of the scattering angle and Compton's formula. Compton's derivation treated the electron as a point particle, not a ball of charge, and he showed that a ball of charge was inconsistent with his results. Previously, he and some other physicists thought they could explain some phenomena by the electron being a finite ball of charge. But he did not need that to explain his results, and in fact, he showed that the electron could not be a ball of charge and produce his results. Compton did not need any new constants in order for his work. This is a possible time to take a break. The Dubrow matter wavelength, 1924. Louis Dubrow was a French physics PhD student in 1924. Many of us don't speak French, and we probably pronounce his name as Broglie. You will certainly hear some physics professors pronounce it that way, but my understanding is that we should pronounce it as Dubrow. In 1924, he published his PhD thesis, and that is the basis for this material. Recall that electromagnetic waves exhibit some particle-like behavior. We saw that in the photoelectric effect, and we just saw that in Compton scattering. Recall that the photon has a momentum P equals h over its wavelength lambda. Dubrow's PhD thesis proposed the wave-particle duality hypothesis that matter particles can display wave-like behaviors under certain circumstances, just as electromagnetic wave photons display particle-like behaviors under some circumstances. And he called these waves of matter particles matter waves. They're also called Dubrow waves. For photons, we had that the momentum equals Planck's constant over the wavelength. So Dubrow inverted this to say, for matter, we know its momentum, so let's use that to calculate its wavelength. So the matter wavelength lambda will be Planck's constant over the momentum. So h over mv for a non-relativistic matter particle. Dubrow also addressed relativistic motion. We're not going to worry about that. We now call this the Dubrow relation and the Dubrow wavelength, where h is Planck's constant, not h bar. M is the object's mass. P is the object's momentum, which could be relativistic, but if it's slow compared to the speed of light, we can use mv, where v is the object's speed, for a non-relativistic particle. His paper addressed frequency of matter waves, but we're not going to use those results. We're not going to calculate a matter frequency for a particle or object. This is a possible time to take a break. If the matter wavelength lambda is comparable to or larger than the object size, the system, or features of the system, for example, slits, the object might behave like a matter wave and show wave-like aspects. In this case, we should use quantum mechanics and Schrödinger's equation. In 1927, the diffraction of electron matter waves, electron diffraction, was detected by Davison and Germer by firing electrons at a nickel crystal. So it's not just theoretical. There are experiments in which matter particles do behave like waves. If lambda is much, much smaller than the object size, the system, and features of the system, for example, slits, the object might behave classically and we might not need quantum mechanics. This is a possible time to take a break. Let's do a bunch of examples so we get more familiar with this wavelength equation. In the 1927 Davison-Germer experiment, They used experiments on electrons that were accelerated through 54-volt potentials, so they ended up with 54 electron volt kinetic energy. And those electrons were fired into a nickel crystal, which had a periodicity between atoms of 0.91 angstroms. For 54 electron volt kinetic energy, the electron speed is 4.4 million meters per second, and that is not relativistic. So it's small compared to the speed of light. So we can plug into the formula lambda equals h over mv. We know the value for h, we know the value for the electron mass, we have the speed for these electrons, we plug it in, and we get a wavelength of 1.65 angstroms. This wavelength is comparable to or larger than the 0.91 angstrom periodicity of the nickel crystal. So these electrons have wave-like behavior, diffraction, in this experiment, and we should use quantum mechanics, not classical mechanics, to describe their behavior. The experiment can also be done with neutrons, room temperature neutrons, thermal neutrons, have a speed of 2.2 thousand meters per second. They have this mass, this velocity, so their wavelength is 1.8 angstroms. And that has been observed. The diffraction of thermal neutrons has been observed. Now, we're used to thinking that quantum mechanical things only operate on the scale of an electron or an atom, but molecules of 600 atomic mass units, so the weight of 600 protons and neutrons, a molecular beam of those molecules traveling at 100 meters per second, that has a wavelength of 0.067 angstroms, and diffraction of those molecules has been observed. In fact, molecules with 810 atoms and 10,100 atomic mass units of mass, they have been observed to interfere in diffraction experiments. So even pretty substantial molecules can be made to show wave-like behavior. This is a possible time to take a break. How about an electron bound in an atom, bound in a hydrogen atom, orbiting the nucleus at 2.2 million meters per second? Now, I've said before that the electron doesn't really orbit the nucleus, but we'll use this speed from the Bohr model. Planck's constant, mass of the electron, speed of the electron, wavelength of 3.3 angstroms. That is comparable to or larger than the size of the atom. It's larger than the size of the atom. So that electron has wave-like behavior, and we must use quantum mechanics to describe its behavior. How about a free electron, an unbound electron, moving at 100,000 meters per second in a 1 micron thick film of aluminum. When we calculate that wavelength, we get a wavelength of 6.1 nanometers, or 61 angstroms. It's larger than the size of an atom, but it is less than 1% of the thickness of the aluminum film. So classical physics might suffice to describe this electron. How about a baseball thrown at 90 miles an hour? A fastball. Mass is 0.145 kilograms. 90 miles an hour is 40 meters per second. Plug in here and we get 1 times 10 to the minus 34 meters. Greatly smaller than an atom or even a nucleus. So that baseball, classical physics suffices to describe this fastball. This is a possible time to take a break. Now, there are some difficulties with using the Dubrow wavelength. The observed speed and the calculated wavelengths, they depend on the speed of the object, and different observers moving relative to one another will see different speeds, and they will calculate different wavelengths. So two observers could draw opposite conclusions about whether the object is probably in the classical versus quantum behavior regime. That's a little strange. But much worse than that, if the speed is 0 and we plug it into that equation, the Dubrow wavelength will be infinite. And if the wavelength is very large, we should have to treat the system as quantum mechanical, but the behavior is typically still classical. Consider holding a baseball in your hand so it's not moving. You see the baseball, it's solid, it's definite, it's not a wave. So beware using the Dubrow wavelength, especially at really low speeds. The Dubrow wavelength is not a valid measure of the size of a particle at all. That's not what, it's a length, but it's not the size of the particle. The Dubrow wavelength and wave-particle duality might not apply to objects heavier than a certain mass that gets the name Planck mass, 2 times 10 to the minus 8 kilograms. We're not going to worry about that, however. The speed and frequency of the matter waves are somewhat problematic, so we're going to ignore these, and I didn't cover them. They are in Dubrow's PhD thesis, however. We should not think that matter waves are the final description of reality. We should use quantum mechanics and Schrödinger's equation when we need to describe particles or systems. So Dubrow's 1924 wave-particle duality hypothesis and the Dubrow relation and wavelength, they substantially influenced Schrödinger's 1925 development of the Schrödinger equation. And the Schrödinger equation is more correct than using the Dubrow wavelength. This is the end of lecture B5.